Good morning.
Good morning.
Hey, good morning.
How is y'all today?
Doing good.
Cool. Let me give everybody a second here. Throwing one note we might need into my access so you guys can see it. Let's turn off the music. Feels like a long time since we were together last. For some reason. Technology is working. What are we doing today? We are doing something in chapter 13 called the dot product. And to illustrate this, I want to give you kind of a, I don't know, wake yourself up and see if you can do this problem. I'm going to just draw future math teachers. This is what a warm-up is. Get people thinking, get their brain alive. Help them understand what they're talking about today. So I'm going to give you a couple of vectors. The vector 2, 10, let's do that one. 2, 2, 4, 6, 8, 10. So there's the vector 2, 10. Come on, straighten it out for me. Can't have an ugly vector like that. It's early in the morning. So that's the vector 2, 10. Notice I chose to draw it from 0, 0. And then let's also consider the vector 7, 3. And you don't need to know anything new today to be able to tell me what is that angle right there. So I want to give you a second to see if you can pull that off. And if you're not often rolling, you should be thinking of what is the angle of each vector individually and then subtract them. Did that occur to you? So I made this very easy. I'm wondering if you have already figured it out. But I'd like to give you a really good, that was my goal, to give you a really good, not procedural, but conceptual understanding of these things. And because these vectors are always creating, if you will, right triangles, of course, with this distance being 2 and this distance being 10, then I guess I could say the red one, I'll call the red one phi. If I said the tangent of phi, that would be opposite over adjacent. So the inverse tangent, I'm going to do this in degrees just because that's a nice way of talking about angles. So I got 78.7 for phi. Maybe you did the same thing. And that looks right because that's a fairly large angle right there. I'll label it. Yeah, that seems to fit. I don't see anything wrong with that statement. And then you say, okay, well, this is easy. I don't need to know anything new. Let's use alpha for this angle. And because it was over 7 and up 3, that means the tangent of alpha is opposite over adjacent. If you say take the inverse tangent of 3 divided by 7, you get 23.2 degrees. And so you say, okay, that's easy. Then all I've got to do to get theta is subtract those two. So I guess I won't even rewrite the angles. If I take phi minus alpha, then see, I can do that in my head, 55.5. Wow, that's interesting. Came up all fives. And so there's theta. You agree with that? Did I go too fast? Did I give you enough time to figure that out on your own? I hope. Okay, cool. So that's not really anything new. And so, what does this have to do with dot product? I really don't need anything new. But what I'd like you to do is just to consider now kind of a second question. What if I gave you these two vectors, 4, 6, and -8, 2? If you were not able to do that first one on your own, which you should have been, but if you weren't, maybe I warmed you up enough that you can do this one now. But you should notice this one's going to be worse, and I want you to think about why. draw a rough sketch of it, make sure it makes sense. So what you should be noticing, if you haven't already, is that you had to work a little harder for the one in the second quadrant. So if I said the tangent, the inverse tangent of 6/4 for kind of the first vector, second tangent of 6/4, I got 56.3 degrees. But if I did the same thing for the next one, if I said the inverse tangent of 2/-8, second tangent of 2 divided by -8. First of all, I got all of a sudden a negative answer, which is troubling. But it's like last time I subtracted those. And so, maybe I'm staring at it now going, well, minus, let's see, 56 minus a -14, that'd be 56 plus 14. So is it 70 degrees? Is that what the answer is? Or certainly isn't negative. But the point is I'm a little bit lost now. It's almost like I have to draw a picture and kind of figure out what's going on. Last time, because they're both in the first quadrant, it kind of just worked really nice. Well, this time it just isn't working so nice. So now I think everything was great, but now I'm suddenly confused. So let's just draw a quick picture of this. So 4, 6. 4, 6 is that one. So this one made perfect sense. It looks right. All right, that's awesome. But then when we go to -8, 2, 4, 6, 8, 2. You should realize what we're after is this angle theta here. But that doesn't look like 70. So it's like last time I subtracted, this time I'm not subtracting. You should understand what's happening here. This is something that's came up before, but remember that inverse tangent doesn't know the difference between the inverse tangent of 2/-8 and the inverse tangent of -2/+8. In other words, had this been 8 -2, it wouldn't have known the difference. And 8 -2, of course, would be over here. So it was actually giving me that. It was giving me the answer in the fourth quadrant. Remember, I warned you on my note sheet, if you're in the second or third quadrant, this isn't going to work. And so you'd say, oh, okay, that's right. This is a little bit different. So that's 14 degrees up from 180. And so this one is actually kind of like 14 degrees over here. I mean, that's kind of what's going on. Oh, okay, you say, all right, I got that figured out now. And so I can still get this, but notice in this case, I actually have to add them up. I mean, the way I drew it anyway. I'd have to add those up and then subtract from 180 to get theta. Or I would have to rename. I mean, I drew in 14 degrees, but I'm not saying that second vector is 14 degrees. I'd have to subtract that from 180. So that'd be 166. So, really the angle all the way over here, this one is 166 degrees. That's what I'd actually call that angle. And then I could subtract, right? I could go 166 minus 56.3 and actually get the answer to this. But notice I just had to think more. And really, this is the idea behind a dot product. So just to at least answer it anyway, what is that? It's 109.7. So I still succeeded. I still figured out the angle between those two vectors, but I just had to do something different this time. And that's what a dot product does. Now I'm going to show you something rather crazy. Here's how a dot product works. So I'm first just going to do it, kind of do the magic of it, if you will. And then I'm going to show you kind of why it works or how it works. Before I do that too, I just want to comment. I'm not sure I agree with the invention of a dot product. Only because can't you still get this? Like if the goal is to find the angle between two vectors, can't you just find the angle for each one of them and draw pictures and be a little careful? There's two answers to things and so forth, and negative tangent, inverse tangent kind of screws things up. But it's like, okay, we'll draw a picture, take a little more time, but you can actually pull it off without knowing anything new. I think there's a really good argument for that. If you're a person that likes to conceptually understand math, to say, I don't need anything new for this. I'm not sure I would disagree with that completely. However, it is kind of cool. So as I said, I actually really haven't decided. Let me show you kind of the dot product method to this approach. So there's a formula that I'm going to build for you in a minute that says the cosine of the angle between two vectors, that's that same theta angle, is equal to, see, I want to use the same language that I did in my note sheet. I guess I'm not going to. Is the dot product of two vectors, and you say, I don't know what a dot product is, divided by, and you should know what this is, the magnitude of two vectors. So if you want to know the angle, you just do those two things, take the inverse, and notice it's kind of weird that tangent's not involved, right? Like, didn't we just need tangent? I mean, weren't the two sides of the vector the legs of the triangle? And so now I'm just going to do this. I'm going to do this to get that 109 a second ago. And so what is a dot product? Well, this is what a dot product is. If I take 4, 6, and I dot it with -8, 2, this is all you do. You take 4 times -8, -32. You take 6 times 2, 12, and you add them together and get -20. There's the dot product of those two vectors. And you know how to find the magnitude of those. So if I say the magnitude of u, of course, that's 4 squared plus 6 squared, that's 16, and 36, which is 52. So that's the square root of 52. And the magnitude of vector v would be 64 and 4, which is the square root of 68. So what you're telling me then, teach, is the cosine of theta is equal to -20 divided by the square root of 52 times the square root of 68. In other words, if I type the inverse cosine of that mess into my calculator, be doing this ahead of me, please, that you will just get, boom, 109.7. Yeah, that's exactly what I'm telling you. So convince yourself that that's true. Be careful how you type that in, because you're either going to need a second set of parentheses around this, as I hope you know. I bring those little things up from time to time, but if you don't type it into your calculator like that, you're not going to get the right answer. But notice the cool thing about this is this little neat formula doesn't care what quadrant you're in. Like you can just take any two vectors and just stick them into this little machine, and then boom, out pops the angle. There's no thinking. There's no like, oops, the inverse tangent doesn't work in this case. Well, it worked in this case, so great. We'll just use the two angles and subtract them. But then over here, it didn't work. We had to do something different. Well, this little formula just says, doesn't matter. Stick them in there, boom, out pops the answer. That's pretty cool. So again, I ask you, what kind of person are you? Do you look at this tool and think, that's really cool? You have a form, you have a machine now that you just sort of plug the two vectors into, and then out pops your answer every time. You don't have to think. Are you the kind of person that goes, that's a tool worth building? That's really cool. I like that. Are you the kind of person that goes, well, yeah, but I don't understand where it came from. I have to memorize this tool. I'd rather just draw pictures and stick with SOHCAHTOA. Like, I already understand that. Again, I think there's a really good argument for both. So in a sense, what I just showed you is kind of how you multiply two vectors together. Like we've been adding them, right? Like we knew how to add them, and we saw that if you add two vectors, like the wind force and the force of the airplane and so forth, that actually adds and tells you where the airplane's actually going to fly. So we saw that adding was super simple and it made sense. But you might have thought, well, multiplying them then would just, well, how would you multiply them? Well, this is how. It's a dot product. But of course, it's very, and I would encourage you after this to go Google search on videos and so forth. What the heck is a dot product? And you might have some trouble kind of figuring it out.
Hey, Doug, does this work with vectors in 3 dimensions?
Yeah. And to your point, Connor, that's one of the arguments for it. Because can you appreciate trying to do what we just did? Well, the slow way here, if it was 3D, the vector was 3D, well, now you're in a world of hurt. And the dot product says, oh, no problem. Yep, easy, can do that, no problem. So if you are looking for an argument to learn this, that would be it. Well said. All right, I'm going to build this tool for you just because I want you to have a conceptual understanding of it. So, and again, I just find these things brilliant. I mean, who thinks of these things, or who looks at it this way? Well, let's see if we can build it. Build the dot product. And you may have noticed too, right here, that dot, it's really nice that I drew it as a circle, because that's a symbol we haven't used before. You'll see it in your book. You won't see it in your book too often as an open circle dot like that. A lot of times you'll just see it as, well, just the same old multiplication dot you've ever seen before. And that's actually still okay, in the sense that, how do you multiply two vectors? Well, it turns out that's what you do. You multiply the x's with the x's and the y's with the y's, and then you add them. It could have just as easily been multiply x's with x's and y's with y's, and then multiply those two answers. Like, why would addition get involved? But just be aware of that in terms of symbols. On all my note sheets, I'm actually going to draw a genuine dot, just because it helps me kind of remember, oh yeah, this is a little bit of a different process. But here's the idea. Let's see if you can handle this brilliance. And I'll even do this in 3 dimensions. So let's say, just like a second ago, you kind of have these like poking over in different directions. And I'm going to call this one vector B. And I'm going to label its components B1, B2, B3, just so we can keep them straight. And then, of course, I'm going to name this one vector A, and I'm going to name its components. Its X is A1, its Y is A2, and its Z is A3. So now it's kind of easy to tell which one goes with which. And of course, what we're after is this angle that's between them right here. And, I drew it as 2 dimensions, but you could imagine if I could flip it around and so forth, 3 would be even nicer. And does it make sense if we could actually create a triangle up here? Like this? Then we'd have a non-right triangle, but we know things about non-right triangles, right? Like law of sines and law of cosines. But the question is, what is that blue distance right there? Do you understand that it's not A plus B? Notice these two vectors are drawn tail to tail right now. And so I'm going to erase this, but if I moved B up here, then isn't that B? That's also vector B. And so wouldn't this be actually A plus B? Like it's totally going the wrong direction. You see what I'm saying? Like that doesn't work at all. But here's something really cool. What if you took vector B and made it negative? Negative vector B. Well, would you agree that's just the same thing going in the other direction? So then what if I said I want A plus negative B or just A minus B? Well, then wouldn't you be taking A first over here, but then you'd be taking off in that direction right there. So there's vector negative B. So if you go A plus negative B, then isn't that this vector right there? Oh, we just found it, didn't we? That's vector A minus B. So there is a way to actually kind of consider two vectors that are tail to tail. And notice it does have a direction to it. So it's actually going that direction. So now we have a name for it. And so what now we can actually, well, we can consider something. If remember, we're trying to use this to try to find this angle. And so we need a formula for that non-right triangle. Right triangle. We need a formula for that non-right triangle that involves that angle. And notice we can know the lengths of all the sides. And so we know one angle, or at least there's one angle that we'd like to know. And we have a way of writing down the lengths of all the sides based on magnitude. And so this is a classic example of a place to use the law of cosines. So let's see if you can survive this. The law of cosines. So in this non-right triangle up here, the law of cosines would say, let's see, the side across from the angle is A minus B. So the length of A minus B, the magnitude, in other words, because remember, it's not the vector itself, it's the length of the vector. We're talking about distances when we talk about the law of cosines. So that length squared would be equal to the other lengths squared minus 2 times each of the lengths times the cosine of the angle across. This is why it was very important that the A minus B is the one that's by itself, because remember, this part of it here kind of looks like the Pythagorean theorem. So this one was by itself, and therefore the angle over here has to be the one that's across from it. So that's very important that I got that right. Okay. So at least right now you can already kind of see in a sense where this is going, because didn't this formula right here that I just told you, like it didn't have a cosine in it, and it's like that's how it got there because of the law of cosines. And so you can at least see where this is going. But let's just go do some of this stuff. Let's go find these magnitudes. Well, first of all, can we do the distance formula for all of these? Well, you know how to subtract vectors. Like if you go A minus B, let's write that out up here just because we got a little bit of space. If I said I need vector A minus vector B, well, don't you go each component minus? In other words, isn't it A1 minus B1? That's how you get the X component, right? Whatever their X components are, you subtract them. And then whatever their Y components are, you subtract those. And then whatever their Z components are, you subtract those. And so there's A minus B, right? Vector A minus B. But again, what do we got to do to find the magnitude of something? Don't we have to square those things and then add them together? So if I square those, A1 minus B1 and A2 minus B2 and A3 minus B3, I square all of those and I add them together and take the square root. Isn't that the magnitude of that vector? And now I'm going to continue. What about this one? Well, isn't that the A1 value squared plus the A2 value? It's just the components of it. It's a little easier and quicker to write down, plus A3, all of those squared and added together and square rooted. And then the B plus, then we'd have a B1 squared plus B2 squared plus B3 squared, all square rooted. And then minus 2 times all of that again. Wait a second, what's wrong with what I said here? What's wrong with what I wrote? Come on, we warmed up already. We should be warm. What did I leave off? Here's a hint. Did I ever do that?
So you get a square every.
So I got to square those, which means those square roots are actually gone, right? So, okay. Again, this feel like it's going nowhere, because I mean, this is a gigantic formula. This is not helpful. At this point, I'm thinking, forget it. I'm now in the let's just do it the old-fashioned way camp. I don't want a dot product and all that nonsense. But watch what happens here if you don't quit with the algebra. Well, I'll do this a little on the quick side because I've got to assume you're decent in algebra. So I'm just taking these terms now. Isn't that A1 squared minus 2A1B1 plus B1 squared? And then plus the next one, which would be A2 squared minus 2A2B2 plus B2 squared. And then this next one, which is plus A3 squared minus 2A3B3 plus B3 squared. Why is that suddenly looking brighter? Do you see it? Well, look, there's an A1 squared and an A1 squared on both sides, so I can subtract them away. There's a B1 squared and a B1 squared on both sides, so I can subtract them from both sides. There's an A2 squared and an A2 squared on both sides, subtract them away. B2, B2, A3, A3, B3, B3. Ooh. Now what do we have? Well, we have -2. Notice every one of these has a -2. I think I'll save a little time and factor it out. -2, and then there's an A1 B1 plus an A2 B2 plus an A3 B3. And on the other side, you just have the rest of what was over there, which is all of this equals all of this. That's the only thing that was left. Everything else canceled out. We're getting close. I don't know how you just got there, but go away. So now, hey, look, they both have -2. I could divide -2 away from both sides. The question is, are you seeing the formula now? Now, I only showed it to you once, but let's go back up and look at it again. What did this formula say the cosine of theta was equal to? The dot product divided by the magnitude of the vectors? Are you seeing that here?
I see it.
Seeing it, I'm feeling it. So cosine of theta, if I wanted to solve for it, I'd have to divide those two square roots over to the other side. Which I do not want to rewrite. And so we have it. So this is nothing more than just the magnitude of A. This is nothing more than just the magnitude of B. And then when somebody stared at this, they thought, well, what's that new animal? Like, notice it's pretty memorizable. But notice it's like, oh, A1, B1, that's like multiplying the two X coordinates together. And then A2, B2, that's multiplying the two Y coordinates. So somebody just made that up. Made up dot product. Like, let's just call that a dot product. Let's give it a name. That's kind of cool. It's kind of useful. We got to memorize it. That's why people don't understand it. If I say, what is a dot product? It's a mnemonic device. That's all it is. It's just something that tells us to do that right there. So don't expect to understand what a dot product is. It's a mnemonic device. It's a memorization tool. That's all it is. Let's call this the dot product. So, and notice it seems to be working in 3 dimensions, if you will. I did it in 3 dimensions on purpose, and you can appreciate, I really don't think this would be possible if you didn't do this in 3 dimensions. I don't know if that makes sense to you, but let's take a look at it, and let's take a look at this in GeoGebra with an example. So let's see if you can use it. I'm just going to make this up randomly. So, and I'll go back to different letters. Let's say vector u is equal to 3, -2, 6. And vector v is equal to -4, 1, and let's go 2. Can you find theta using the dot product? 3-dimensional trigonometry is very difficult. You'd have to draw right triangles in 3 dimensions to get this. I almost want to say it's impossible. So some of these tools are actually designed to help you work in the real world, which is 3 dimensions. Six. Let's see, is there some reset button to this? That's what it was. What is it? Sweet. Okay, I turned it sideways. Notice I have the luxury of being able to spin this in such a way that you can actually see the angle. Notice those two vectors are in some weird plane that isn't parallel to the X or the Y axis. But I don't know about you, but I would say that's just a hair over 90. Did you get 95 degrees, 97? I don't know, I'm guessing.
93.
93. So that looks reasonable, doesn't it? So can you appreciate that? I almost want to say this wouldn't be possible with regular trig. Does it make sense you'd actually have to establish the plane that this thing is actually sitting in order to find the angle between them? Can you appreciate how hard that would be? Like, what is that plane? What angle am I at? My brain starts smoking just thinking about what that might be. So yeah, I'd say 93 degrees is pretty reasonable. I just made that up, but so I don't know the answer, but that's pretty powerful. And again, just as a reminder, notice GeoGebra, how it lists the vector. And I kind of like that. I kind of like listing it vertically like that because it doesn't look like an ordered pair. And it's still just using parentheses. So you can just use normal parentheses. And of course, it's in order, X on top and then Y in the middle and Z on the bottom. And so pretty cool. Notice that really wasn't much trouble. Like a dot product in 3 dimensions, you know, what do you got to do? Multiply one extra set of numbers. Is it really that hard? And then the Pythagorean theorem, same thing. It's like, oh, I just got one more number to square. Like that really was not very much trouble. So that's an amazing tool. Works in any dimension. Okay. Let's see, what questions do you have or thoughts do you have on this matter? I'm assuming your silence is none. I'm happy. Is that true? So
I got none.
no problem with that. Neat. If your thought is like neat, everybody agree with that? I think that was Raymond that said 93 degrees, but I'm not.
Yeah, that's what I got.
Sweet. So works in 3D. A little bit, I mean, it occurred to me the other day, I was just thinking about, because I've done a lot of construction work and there's tools in construction, like a hammer. And does it make sense if you said, I got to pound this nail in? I mean, you kind of have two choices. If you're just kind of sitting there, you could think, well, there's a rock. I'll use that rock and pound it in, which actually would work, wouldn't it? And it's right there and it's at hand and I can use it. But if I have a lot of nails to pound, it might be worth the time to like not pound any nails for 2 hours and go build yourself a tool that from then on would pound those nails like really easy. I mean, that's kind of what you do in math. That's what mathematicians do. They stop and build a tool. But of course, now it's like tools break and you got to know how to use them. And that's the part of math that's kind of hard. So let's grab. So I posted this already in my open math for you, but just so that you understand, you know, what you're going to have on this next test. It's not something I want you to memorize. Let's just think about what we've learned so far here. You know how to find the vector, you know how to find the magnitude of a vector, because we're kind of going 3D in this section though. So that's not anything new. Dot product. Notice I wrote it in this way because I want to show you something about that in a little bit. But dot product is used for the angle between a couple of vectors. And notice I wrote it, if you will, a little bit differently. And I'm going to show you why in just a second. And then I just told you, like, what is a dot product? And notice I just see that I did something kind of dumb here. Like I changed this to a dot, but then I didn't do it down here. Actually, maybe in hindsight, that's a good idea, just because that's what you're going to see in your book. There's not an easy way to go get one of these dots, if you will, in normal books. And so isn't that what we said? Yeah, look, multiply the X's, multiply the Y's, multiply the Z's, and add them all together. That's what a dot product is. So that's the only thing that's new. There's a few other things that we'll be getting to in the next couple of days. What about a cross product? What about a projection of U onto V? We're probably going to get to that projection thing in just a minute. But I want you to, I wrote it this way on purpose, and I'd like you to stare at that for just a second. In a sense, that's the definition of a dot product. That's exactly why I wrote it that way. That's not really written in the way to solve for theta. In other words, if you're trying to find theta, you might want to say, well, what I said earlier, cosine of theta equals, and write the rest of it out. But if somebody says, what is a dot product? Well, notice it's kind of like I have two answers to this. Well, one of them is down here, and then the other one's right there. So it's like vector u times vector v times the cosine of the angle. Like, what the heck is that? What is that? What does that mean? But I just want to highlight that for a second for you. Let's do that. And one of the reasons I did not understand a dot product very quickly in terms of like conceptually, what is it, was because nobody ever told me, or I couldn't find any simple explanation like I gave you, where somebody said, it's not anything. It's a mnemonic device. It's a cool way of memorizing a part of the process that just happened to organically arise from the law of cosines in that picture. That's it. It's just it's neat. Like, it wasn't just a bunch of random numbers everywhere, right? It was like, oh, look at that. X's times X's, Y's times Y's. Hey, that's kind of cool. I need to memorize that. Well, let's give it a name then. So it said that U dot V was equal to, I think it was, I'm going to write it a little differently. U times the cosine of theta times V. Now, here's exactly my concern is, see that multiplication sign? Is that a dot product? Or is that just regular multiplication? Do you see what I mean? Like, that's one of the things that bothers me. It's kind of why I like the dots. Well, notice over here, because we're saying a magnitude, because of this is a magnitude, therefore that statement is actually just a number. Does that make sense? It's not a vector anymore, it's actually a number, because we're saying I'm going to take those coordinates and make a length out of it, right? So that's one of the things that you're going to find yourself having to, deepen your conceptual understanding of kind of what a vector is. And then, oh yeah, magnitude, what does that do? Oh, that tells me the length of the vector. Oh yeah, okay, that makes sense. So notice that in a sense, there's no danger of misunderstanding if you actually slow down a little bit, or you actually understand what you're doing. Is that right there a dot product? No, because there's no vectors over there. It's just numbers, right? It's like three numbers multiplied together. But I just want to draw you a picture of what that might actually look like. And honestly, this is actually, in one sense, almost not helpful, but I'll show you what I mean. So let's say this is vector V over here. Notice I'm just purposely drawing it level, and this is vector U up here. What I want to know is, what does that tell you in this picture right here? If you take vector U, magnitude U, and just for a second, I'm going to erase this, but let's just pretend, this is like length 10, and this is like length 14 or something like that. That's what those magnitudes are, right? They're just numbers. So if I take the cosine of the angle here, this angle that's between those two vectors, if I take the cosine of that and multiply it by 10, what is that actually telling me? I want one of you to tell me. SOHCAHTOA, or right triangles. What if I take 10 and multiplied by pretending I know the angle?
That's side angle side, right?
Which side is it?
Hypotenuse?
10 is. 10's the hypotenuse. If you, like, if you're going to take the cosine of theta, then it means there's a right triangle. Does that make sense? No such thing as a cosine of an angle if you don't have a right triangle. So there it is. So now 10's the hypotenuse, and there's the angle. And V is just there to kind of be the bottom of the triangle, if you will. Notice length 14 is not part of that triangle. What does the cosine of that angle multiplied by 10 actually tell you?
The length of the adjacent leg?
That's exactly right. It tells you that length right there, doesn't it? You agree with that? Now, so that actually makes all kinds of sense. In other words, that chunk of it, and again, I'm drawing a two-dimensional picture of this, but that chunk of it is kind of like, well, the projection of vector u down onto, well, the other direction. Now, if I then say I'm going to multiply them, that doesn't make any sense. Like, what good does it do? Let's pretend this length down here is like 8 now, right? Something smaller than 10. So now you're going to say, okay, it's 8 times 14. That's what the dot product is 8 times 14. Like, what? It's one length multiplied by another length. Now, that doesn't make a lot of sense. But remember that these lengths don't have to be lengths. Like, these are forces oftentimes. And so this is one of the places this gets used a ton in physics. So the classic, just kind of simple example, and I'm going to erase this just so that it doesn't make the notes look weird. But what if I said this was like 100 pounds of force and you were pulling in that direction on something? And again, these are the classic boring physics problems where some kid's got a box and he's pulling 100 pounds in that direction. And so the question is, like, how much of that force is actually going to slide the box down the street, so to speak? Does it make sense you don't get all 100 because you're sort of pulling wastefully at a weird angle? And so that might drop to, say, 80 pounds that actually kind of pull the box along. And in physics, you talk about, okay, well, then will it slide because there's friction on the box, and how fast will it go, and what's its velocity, velocity and acceleration. And you kind of play around with that. And, you try to keep it simple by talking about a box with a rope being pulled on it and so forth. But all kinds of applications to this in terms of, like a tractor pushing with a blade, trying to push dirt in a pile, and, things that are actually real, useful. But I just want you to kind of see that just conceptually, but all I'm saying is I don't know how helpful that is. Like, oh, that's what a dot product is. Well, it was helpful just to realize that u cosine of theta was the part of u that was aiming in the same direction as v. And I'm really happy. And then you say, okay, now we're going to multiply them together. Like, what? What do you mean we're going to multiply them together? What does that do? So that's rough. So honestly, the explanations I read for it, I found myself going, that's worse. Like, that doesn't help me make sense of this. Keep it at a mnemonic device. But it turns out a cross product is related to this. And so we'll talk about that. We'll get into that a little bit more tomorrow. But for now, I think that's kind of worth something. So it's kind of the part of you that's projected, and that I think is maybe worth keeping track of. So it's kind of like the part of you projected onto and I hope you understand this, but it wouldn't matter if we flipped them. Like, it doesn't matter which I put u there being multiplied with cosine, and I drew it a little shorter just so the picture looked nice, but you could project v onto u as well. Like, how much of that 14 is actually going in the direction of u? We could do the same thing and take 14 times the cosine of the angle, and it would accomplish the same thing. So it doesn't matter which of those is which. So other than a mnemonic device, that's the only other kind of, what is a dot product kind of a statement that I could kind of add. Or what does it actually do? But as I said, we're not done because now you got to multiply them. Does that make sense? And that's where it's like, doesn't help. I think it's worse. Now, you'll notice your assignment to this end is actually pretty simple. Well, except for one thing. Let's make up another problem. There's kind of a cool question that I haven't seen in a book before that I saw in my open math. And so I hopefully assigned it to you. This is kind of a neat application to this. Let's see. Let's come up with something kind of interesting here. I'm going to call this an application in quotes because I never believe things are applications unless somebody really uses them for something. And I haven't put enough thought into this to know if anybody does. So let's consider two equations. Let's see, let's make up a parabola. Let's keep it kind of simple. X squared plus 2x. Let's see, I want to make these go through a nice point, like x is 2. If I put x is 2 in there, that becomes 8. So then if I say minus 5, 8 minus 5 is 3. So would you agree the point 2, 3 is one of the points on that curve? And again, I'm purposely making this up live just so that you can think it through with me and learn to make up problems yourself. You don't have to rely on a book to make problems up. You can make them up yourself. So the point 2, 3 is on that graph. And that's a parabola, it's a curve. And so I'd also like to come up with a second equation here that also goes through that point. And I want to give it kind of a slope. Let's see, 2, 3. So it's probably, I don't know, over here somewhere. So let's make like a low sloping line that runs through that. So like a slope of, I don't know, let's say a half x. Well, I also want it to go through the point 2, 3. So let's see if I put 2 in there, that's 1. And then if I add 2 to it, then that'd be 3. And so there, I just found two curves that hit each other at 2, 3. And now I'm going to make a slightly nicer graph of this. So the line. And I'll tell you while I'm kind of playing with this a little bit, what I want you to do is find the angle. Like, how do these hit each other? How do these two curves hit each other? So there's the red line. And now the blue curve, x squared plus 2x minus 5. So 2, 3, that's where they hit right there. That's kind of cool. And 0, -5 is where this thing emanates from. So we're talking about a parabola. It's actually not necessarily true. 0, 2, 3. 1 would be -2. 1, -2. So actually, I don't really know where this parabola is for sure. I thought it bottomed out on the. So maybe it looks something like that. I don't know. What I'm interested in then is well, notice there's two choices here for the angle. I say, what's the angle between them? There's an acute one and an obtuse one that's more than 90 and one that's less than 90. I want the kind of the simple one, the natural one, the one that is obvious. I want the acute. Find the acute angle. And of course, it's particularly cool that one of them is curved, right? Like I could have made two lines and asked you where they hit, what the angle was between the two lines. But notice it's like, these are not vectors. Like we got to make vectors out of them. Does that make sense to you? How are we going to make a vector? How are we going to make our own vector out of these? That's kind of weird. So I'm going to call this vector L for line instead of U or V or whatever. Can you make a vector out of that? Do you understand that everybody in class makes a different answer to this question? What's the easiest possible vector you could make out of it? Remember, it's just a question of how far in X and how far in Y from the point that you choose to start at. Now, I drew it starting from the Y intersection of 2 here, but it's not like you have to start from there. Pick any point you want, but isn't the easiest, since I started from here and went to the point 2, 3, isn't that right 2 and up 1? So isn't this a really easy answer to the question? But you could also pick over 4 up 2, over 6 up 3, over 9 up 4.5 if you're not afraid of decimals and fractions. So I made a vector out of that, but notice it doesn't actually matter how long it is, because in this case, we're just talking about the angle between them. Might be fun to play around with. Really, would I get the same answer if I did it with 4, 2 as if I did it with 2, 1? That's kind of weird. You may also notice it's entirely just based on the slope, isn't it? Like, isn't the line, the slope is 1 over 2, a rise of 1 and a run of 2. 1 is the Y, the rise, and 2 is the run. And so that's where the 2, 1 came from. Like, that's the easiest answer I could get. Well, maybe that gives you a hint about the parabola, because the parabola is curved. So this should bother you, right? There's actually no such thing as the angle between a curve and a line. What do I need to do? Because the angle is actually getting bigger and bigger, isn't it? It's like not staying the same.
Take the tangent line at the point of convergence.
Yeah. I got to come up with a line for that myself, which is easy thanks to calculus. In other words, and I'll draw it a little wonky, but that is an angle I could come up with right there. So I need the slope. I need the slope of that line. Well, you know, calculus, slope of that line is the derivative. The derivative of x squared plus 2x minus 5 is 2x plus 2. So you now have a slope finding equation, but of course I need the slope at x is 2. Since the recipe for slope here only calls for x, then I only need x. Since the coordinates of this point are 2, 3, so I throw 2 in there and I end up with 6. So y prime at 2 is 6. The slope is 6. Well, isn't the slope all you need to write a vector for it then? What would a vector, I'll call this P. What would the vector name for that be? It'd be easy to mix this up because you want rise over run. You want y to be correct. You're going up 6 and over 1. So 6 is the y, 1 is the x. So again, 1, 6 would be the easiest possible answer. Well, now I have a couple of vectors, and then you can do the dot product and find the angle. Now, I made a fairly rough graph of this, but I'd say that's a hair over 45 degrees. It looks a little more than 45, but maybe I'm wrong. Maybe it's 40, but it's in the vicinity of 45. I'm just guessing, but I think it looks a little bit bigger than 45. So now I say, oh, well, I just made 2 vectors. And so that's kind of cool. You know, where does one path run into another path? Where does a curve, what angle do 2 curves hit each other at, so to speak? That's kind of cool that you could, you know, make an application out of that. I say application because I want to, you know, I want somebody building a road to need this. To me, then it turns into an application. But if it's just curiosity, then application in quotes. Oh, this is easy. I can almost do this in my head then. So the cosine of theta is equal to the dot product. I can do that in my head. 1 times 2 plus 1 times 6. That's 8. The magnitude, notice you're multiplying these, so it doesn't even matter which one is which. The magnitude of 2, 1. Pythagorean theorem on 2, 1 would be the square root of 5. The magnitude on 6, 1 would be 36 and 1 or 37. So the inverse cosine of 8. And by the way, an easier way to type this is just to say 8 divided by the square root of 5 divided by the square root of 37. Had you thought of that before? Just because then you don't have to put an extra set of parentheses because they're both divided, right? Is it this? The square root of 37 is also on the bottom. So if I just say 8 divided by the square root of 5 divided by the square root of 37, and then close off that parenthesis. Notice how my guess was decent. I said it looks like it's more than 45. I got 53.97.
That's what I got.
So approximately 54 degrees. And so I'm always encouraging you to estimate. I estimated first because now that I got this answer, I think, well, I probably didn't screw that up. Incidentally, can anybody think of a genuine application? Like somebody would want to know this? My first thought was like things fly through the shape in parabolas sometimes. And so, you know, the path of something in space, that's a little, perhaps you can appreciate because one of the things I've showed you is it kind of makes it look like vectors are hitting each other. But does it make sense in space? You know, one thing is on this path over here, another thing is on this path over here. So they don't run into each other. You know what I'm saying? Like it's actually really unlikely that two things in space would ever even cross the same path, let alone be at the same point in the same time and run into each other. Anybody know what that's called? If you have two lines or two vectors or paths and they don't even touch each other at all. It's kind of a weird name. You only hear in like a geometry class, but it's called skew.
Oh, okay.
Skew, like parallel is when, you know, when they're in the same plane, but they don't hit. But skew is kind of cool because if they're not in the same plane, they still don't have to hit. Now, if they're vectors, does it make sense you can move them? And then you can still talk about the angle between them. That's what's kind of cool about a vector because it's like a force. But my point was my application of like, what's the angle between that, you know, satellite flying up there and so forth? It's like, well, they didn't even touch. So that's a dumb question. That's not really a good application. So let's take a quick look at this. We'll get started on this, but we have a little time tomorrow to look at this too. But the projection of U onto V, that's exactly what we just did a second ago. The projection of U onto V. So let's take a look at that and then we'll quit. And really what this is, as I said, I already kind of introduced it to yourself, to us. So, you know, what is an application for the dot product? We saw that it would find the angle between two vectors. That's its primarily application. So find theta. There's a second one that is this projection business. And I showed you why in physics, why that's kind of cool, because you're pulling at the wrong angle, so to speak. And so, you know, what part of it is in that direction? By the way, it's really cool situation here. You're on this road, you're driving, you're going 92 miles per hour. If there is a cop over here, officer of the law, this is the direction that the radar gun will be looking at your speed. Do you understand that? Cops do not sit off to the side of the road like that. Cops sit right next to the road. They're like behind bushes, those kinds of things. They sit really close to the road. What we're talking about here is really the projection of 92 degrees or 92 miles per hour. So we'll call this, you know, vector U, as in, well, U. And this is vector V for the cop. So what we just looked at a second ago is, maybe I think it's okay. If I draw this right here, that is the projection of U onto V. That's how you say that. The cop is not going to see 92. Does that make sense? Now, just for the fun of it, let's say the cop was sitting there so that this angle was, well, what does it look like? Maybe 40 degrees. Does that look about right to you? As I said, this is not difficult. What did we just do a second ago? I take 92 times the cosine of 40. 92 times the cosine of 40. And you are going 70 miles per hour and you won't get a ticket. Does that make sense? Like you're going 92, but does the cop know that? Is there any way for his radar gun to detect that? The answer is no. And that's kind of the point of a projection. It's kind of like, well, great, you're pulling at 100 pounds, but you're pulling in such a wastefully stupid direction that nobody's profiting from that. Does that make sense? It's not useful. The only part of your 100-pound pull that's useful is multiplied by the cosine. Maybe it's only 70 pounds or something. And so this is an example of why a projection is such a cool kind of a concept. There's a lot of examples of this. So in cop school, they teach you don't ever be more than 10 degrees. Because if you rerun this at 10 degrees, 92 times the cosine of 10 degrees, then you read 90.6 miles per hour. In other words, it's 91. It's only 1 mile an hour off. So rather than teach a bunch of trig and calculus and physics to a cop, they just say, dude, just sit, make sure your angle is 10 degrees or less, and you'll be fine. Because in the end, of course, they got to be able to, prove, because they're obviously busting you and spending your money. They got to be able to prove that you were really speeding. And so if it doesn't show on the radar gun, then you weren't doing it. Does that make sense? So don't sit there. You can see why they teach that, right? That makes a difference because 70 is a gigantically different number than 92 in terms of speed. That's the idea here. Well, so this isn't really that hard, right? I mean, we just kind of let's see, how do I say this? So let me kind of write out one definition of this: the projection of U onto V. This is the kind of the first, and I want to see if you can understand this. So that'd be U times the cosine of theta. So you agree with that, right? We already did that. However, what is this part of it? You go on to say, you go on to multiply by that quantity right there. What would that be accomplishing? And can you tell me what that is from what we've been studying? Why did I add that? Why did I add this? And what is it? In a sense, those are kind of the same answer. But do you recognize that? This is something we've done, but the question is, do you recognize what it is? Because remember, what this just produced in the picture above is this right here just produced the 70 miles per hour, right? Which is great. That's the important part. Absolutely. 70 miles per hour. And in the case of the cop, that's all you need. You don't need anything else. But what's the rest of that for?
Just the direction, right?
Nice job. How'd you know that? Brainstorm, brain flash. How'd you figure that out?
Well, it would equal 1. So if like the one on the bottom would just be a positive value, and then the one on top would be like whatever direction it's going, I guess.
Yeah, like in the case of a cop, they don't really care what direction you're going, right? As in that application, they wouldn't care what direction you're going. But notice what you really just did is you took a magnitude. Isn't this a magnitude over here? That's a magnitude, but a vector takes a magnitude and a direction because direction does make a difference in lots of applications, right? You're lifting a load. It's like it matters where it goes. So 92 miles per hour is a magnitude and 70 miles per hour is a magnitude. But this is actually the direction of it. And notice it's in the direction of V, but, and I drew that in the picture, right? I drew it in the direction of V, where the cop was aiming, so to speak. I drew it in the direction of V, but do you recognize that as a unit vector? A unit vector is where you take the vector V, whatever it is, which defined where the cop was sitting, it defined the 40-degree angle, but you don't want it to have a size, right? We don't want it to have a length, because remember, you're going to multiply 70 by it. And so if you take vector V, remember vector V is like, X is 2 and Y is 7, it's just a list, but then you divide by the magnitude. Do you remember how that turned it into a unit vector? And that way, when you multiply by 70, you still have 70, but now you're actually telling it on top of that what direction it goes as well. That's why vectors are cool. 70 by itself is just a magnitude. But if you take 70 and multiply it by something, then cool. So that's awesome. 917. Fail. So stare at this for a second. So you should say, great, you just showed us. Thank you for that. You just showed us that formula right there. You just helped us understand what that is. But what's the downside of that formula? Well, it requires you to know theta. That's the downside. Now, the good thing about that formula is you can totally see it doing its work. Does that make sense? You can look at it and go, oh, I see what that's doing. That makes total sense to me, what that's accomplishing. But the problem is you got to find the angle. And you saw that, well, the angle is a dot product, right? Well, where do you think this nicer formula here that does not require the angle? This is nicer. Where did that come from? Because notice that says if you want the projection of U onto V, don't worry about the angle. Just take the dot product of the two vectors and then divide by the magnitude squared and then just multiply by the vector. Just do that and you'll be done. Let's think about that quickly. Do a quick example.
Is that going backwards through the law of cosines?
Yeah, that's kind of right. In other words, it's just going back, and we don't even have to go quite that far back. We just have to, well, replace theta. In other words, this is the formula that we at least made some sense of, hopefully a lot of sense. But does it make sense that we already said that this thing was equal to the dot product of the two vectors divided by the magnitude of the two vectors? I guess I don't need to write the square root because we know what a magnitude is. It involves a square root. Notice there's no symbol between those, meaning if there's no symbol, it means multiply. I could put a multiplication symbol there. So what happens if I replace that? You see the algebra? Do you find yourself saying, so if that's the case, then I'd have that same vector u, but then that would be multiplied by u dot v on the top, and then magnitude of u, magnitude of v on the bottom. And then there's still the last part of this, which was vector v divided by the magnitude of v, all right? So there's our new formula. Oh, look at the wonderful algebra. It saves us a little bit of trouble. Gone, gone. And well, we're done. Except for if I put those together, that'd be squared. And so we just have u dot v, which is what was required to find the angle. And down in the bottom, there's magnitude of v times magnitude of v. Notice it's particularly cool anytime you square a magnitude, because remember, magnitude involves square roots, right? So that's kind of cool that it was squared, because now I don't have to square root it. Instead of the square root of 52, some ridiculous decimal, it's just going to be 52. And then if I just take that, and mathematicians would call this a scalar, which is really just code for, it's just a number. It's a number. You're going to get a number for that. 5, 12. Let's do a quick example. And then you're just going to multiply that by vector v. So what would that look like? So let's project. Let's do a quick example and then we'll be done. So u is, again, let's just keep it 2-dimensional and in the first quadrant, so it's nice and simple. And then we'll practice this a little bit more tomorrow. Like what about 2, 5? And we're going to project that onto maybe a larger, just so you can visualize it. I'm going to project this onto a vector that's below it and a little bit larger. So maybe it goes way out to 8, but it only goes up 3 or something like that. So let's see if we can use this formula. So this is the formula that we're using. So we say, okay, cool. I already know how to do that. What is the projection? And notice there is an order to this, like which one is getting projected onto which one. So the fact that we're projecting u onto v is the reason there's a v at the end of this formula, because that's the direction it's going to go. We need it to go in the direction of v. So we say, okay, cool. That means I take the dot product. That's easy. I take 2 times 8, which is 16, plus 5 times 3, which is 15. So I get 31 for that. That takes care of the top. And then I just need the magnitude of v. Again, that's why it's important to know which one's on the bottom. It's v. What's v? It's the one it's getting projected on to, not the one we're projecting. So the magnitude of v would be 8 squared plus 3 squared, which of course is 64, 9, which is 73. But then we're going to take the square root. But then the amazing thing is we're going to square it. And then we got to multiply that on to vector v. So what's our scalar? Well, I have 31 on top, and I've got the square root of 90. What is that? 64. What did I say? 73. 73. But when I square root it and square it, it just gets rid of that square root. So there's my scalar. In other words, that's the multiplier. That's the number. And so then if I multiply this, maybe you remember why when we learned this in sort of more of a boring example, then I'm really just going to take 8 and 3 and just distribute this to it. In other words, 31 over 73 just gets multiplied by both of these terms and makes them, some small, ridiculous sort of number. So I'm going to write it as a decimal just so that you see what it looks like. It's such, because I made it up, it's such a weird number that it feels like it isn't going to make a lot of sense to me. So I got like 3.4 for x, and 31 times 3 divided by 73. I got 1.3. I'm just rounding these nice. So super quickly, if I just drew that 2583, does it look right? I'm finding myself thinking, and I'm hoping you are too, like what did I just accomplish? I don't even understand what I just did. So the 0.25 is here. So there's vector u, and 8, 3, 2, 4, 6, 8, 3. So there's vector v. And so what we're really talking about is this. If I project straight down, notice that's where the 90-degree angle is. It's not over here. This is not the 90. That's not where the 90 goes. The hypotenuse is preserved, whatever u is. And so this right here is the projection of u onto v. The question is, does that look right to you? is that vector right 3.4 and up 1.3? Right 1 to 3.4 and up 1.3? How come my arrow is not in the right location?
It's just a sketch. You can't draw it like straight for the 90.
Yeah, the problem is I didn't draw a 90-degree angle. In other words, what this is actually saying is, if you had, done this first, would you agree that actually looks like 90 now? So, so it appears to be working. So notice, not only did it give me the size, but it even told me what direction to go. Do you see how cool that is? Again, it's like a tool. You should find yourself going, wow, that's how am I supposed to memorize that? How am I supposed to keep that in my head, so to speak? Well, my class, you're not. Like, look it up, use the tool. But it's just kind of cool to see it actually accomplishing what it was supposed to accomplish. It really did do that. And if I wanted to know the magnitude of it, does it make sense? I could find this magnitude if I want to. In other words, if I'm the cop and I say, I don't care what direction you're going, I want to know how fast you're going. Well, then find the magnitude, 3.4 squared plus 1.3 squared square root. I mean, so that's what's kind of cool about a vector, is it has the XY component so that you know where it's going. But anytime you just say, I don't care where it's going, I just want to know the size, well, then take the magnitude of it. Now you know how fast it's going. So had we done that with the cop problem, we would have basically got a speed in X and a speed in Y, which wouldn't by itself have been that helpful, but that would have told us exactly the direction the cop was sitting at, if you will. So that's kind of cool, isn't it? All right. Let's, I would encourage you to do as I always do, but again, I'll never remember to ask this, so you just got to interrupt. But on your assignment, you actually know everything you need to know to do your 13.3 assignment tonight. Right now, there isn't anything we didn't get to. I only got one quick example. We'll start off tomorrow with a couple of projection problems in 3 dimensions and see if we can actually draw this in GeoGebra and spin it around and go, oh man, look at that, it worked. That's really cool. Just play with it a little bit more. But I think the question in your assignment is only 2-dimensional anyway. But even if it isn't, it's like one extra thing to do. It's amazing how simple it is to take this to 3 dimensions. All right, stay after if you like.
Thanks, Doug.
Thank you all.
And then you said for any dot product, like the circle thing, they just do the regular multiplication sign in like textbooks and stuff.
Yep. And that's because if you took 2 vectors and you said multiply them, you'd be like, what do you mean? How do I do that? I mean, I know how to multiply 5 times 7, but if I said multiply u times v, there's kind of not a way to do it. You know what I'm saying? So
I don't think you can,
yeah,
right?
you really can't. Like, what does multiplication mean in this world? Really, what a dot product is what multiplication means in, well, vector world, where the components, it takes like 2 numbers to describe one vector. Vector u requires 2 numbers to describe it. And so, how do I multiply them? And, what does that even mean? It turns out there's kind of a reason to multiply them. But when you do it in this weird multiply the x's with x's and y's with y's and add them together way. So yeah, you won't see a dot. You'll see a dot in your textbook, not a circle. And I'll kind of use them interchangeably as I'm teaching.
It's kind of annoying that they don't use a circle, but
yeah, that's exactly my thought. Because it just keys you in,
Alrighty, thank you, Doug.
Sayonara, my friends.
See you tomorrow.